So that's a balloon being blown up. Okay, how fast in this balloon blowing up is the volume increasing? Now you've got your strategies in play, which is essentially forming your chain rule. When D diameter is equal to 100 millimeters. Okay, and you're given the volume of sphere, just in case you forgot. So there's a couple of misdirectors here. We're given a diameter and the sphere is R, so we'll need to adjust for that. What's the rate that we're told? I want to write a quotient, d something, d something. What would make sense here? Millimeters per second. Genius. So you're getting confident now, aren't you? You're getting confident. So I'm going to put the millimeters per second over. See how easy it is? Once you recognise what to do, this is not over the top. Okay? The next bit might be a bit trickier, but we'll see. Now, what's the radius? Genius again. Alright, so we're being asked for the volume increasing. So dV dt. We're still going to have dV dt. We're just going to go through something else to get it. And what other things do we have? Well, it looks like we might have something along the lines of dr dt. So it looks like we've got to have a dV dr. Fortuitously, this particular question allows us to take this with respect to r and make our differential. So dV dr is simply going to be differentiating this. So it'll be 2 by 4 over 3 pi 2 off, so it's just r. So we get some cancellations going on here. Not really. 8 on 3 pi r. So there we've got our dV dt is equal to 8 on 3 pi r, that's that guy. And dr dt we have as 3. So straight away we can see that that's going to cancel. So we can cancel this 3. And we've got 8 pi times 50. So I don't know what that is. 5 8 to 4,000. 400 pi. Whatever that is. 3.14 times 4 is 12. Oh, it's up there somewhere. Alright, we can have another one. I'd like one that was a bit more complicated than that, to be honest. I'd like one that requires an implicit Alright, let's try this one. Yeah, this one's a bit of a harder one, but let's have a go at it. So this is for the physicists amongst us. Have you got a textbook for this subject? What is it? Yeah, I don't like you going through the subject without a text though. So P and V as a product are constant. So if P goes up, V will go down. All of those kinds of things. So at a certain instant, okay, so Boyle's law is about pressure and volume. Pressure and volume, their product is constant, so there's going to be changes if the volume goes up or the pressure goes up and vice versa. So at a certain instant we're being given V and P, and the pressure is increasing at 10 kPa per minute. Now it's asking what is the rate of the volume. So it's going to be our interest here is to work out. The trick with this is the units. We've got kilopascals and centimeters cubed. So let's see what we can put together. $720 kPa is 720 times 10 to the 3 pascals. And if we move the decimal place 2, that means that 3's got to become a 5. So 7.2 times 10 to the 5 pascals. Okay, so it feels like you're in physics again. Okay, the volume is 800 centimeters cubed. And if we convert that to meters, we're going to get 8 by, so centi is 2, isn't it? Minus 2. So you're going to get 10 to the minus 4 because it's a volume per meters cubed. So that's quite intimidating, having those two things to be sorted out to get them into base units of pascals and meters. Okay, but I think the physicists will tell you that that's an important thing to do. Now, what's our constant? Our constant is PV, which we just changed them to 7.2 times 10 to the 5 times 8 by 10 to the minus 4. Okay, so that's not too bad. So we can 5 minus 4 is 1, so it's 10. So 7.2 times 8, what's that? $57.6 times 10, so 3 minus 4, sorry, 5 minus 4 is 1, so it'll be 576. Alright, so you've got to get all that stuff out of the way just before you progress, so there is quite a bit to do. Alright, now what are the rates that we've got? We've got the pressure is increasing, so we've got pressure time, so dP dt is equal to 10 kPa. Per minute. Now that's 10 times 10 to the 3 pascals per minute. Now if we want to go to 1, so we can take the k out, then it's just 1 times 10 to the 4. Oh, I'm the long way teacher, so blow it. So we get 10 to the 4 pascals per minute. It feels like physics now, doesn't it? Alright, so that's that one out of the way. And then we've got to think about what's being asked. We're asking for the volume. And forget the decreasing. The volume is meters cubed per time. So we're looking for dV dt. We're still going to have dV dt. We just don't know what it is. And we've already got a dP dt. So it's quite likely that we'll have a dt, but that's a pretty rough assumption. So dV dP, where are we going to get that from? dV dP, because that's the one that we don't have. We have this one, but we don't have dV dP. So who can tell me where we're getting that from? We've got to rearrange this equation. So we've got to put P, make P the subject, COV. Then we can do, oops, maybe it's the other way around. Maybe it's V equals, which one is it? dV dP, so we've got to do it this way. Now if we do the differential of this, we'll have dV dP, which is the one that's missing. So a bit of pre-work before we can get to that, V is equal to Cp to the minus 1. So dV will be minus Cp to the minus 2, which is minus C over P squared. So dV is minus C over P squared, and our dP dt was, I've lost it, 10 to the 4. So C's 576, and we're dividing that by the pressure squared, and the pressure was 7.2 times 10 to the 5. So you wanted a harder one, you got it. Okay, so we process that number, and what do you get? Two fives are 10, 4 on 10, we could subtract them, so we're going to end up with something like meters cubed per minute. So if you think about that in terms of centimeters, no, I'm sticking with minus 11 centimeters per minute. Alright, now with the negative tells you it's decreasing, so you're actually allowed to say 11.1 centimeters cubed per minute as it is decreasing. But I don't think they will have discussed that too much. But converting between the units makes you feel like you're back in physics, doesn't it? Alright, so a little bit of this and that. Alright, what else have we got? Yep, go ahead. Okay, so dV dP, we started off with an equation where the product of the pressure and the volume is a constant. So all we're going to do, and this is a change of units, this is no different to some other thing, alright? So what we want is the volume. So the volume is equal to C over P. Okay? Rewritten, that's like V is a function of P. Okay? In other words, the variable that's changing V is P. Now this is like saying y is equal to C on x. Y as a function of x is being modified by x. So this stuff up the top here is probably familiar to you, but because we've changed pronumerals, this is a bit tricky. So if we now go and differentiate this, okay, we're going to get a result with respect to x. We're doing it exactly the same as we would do it above the line there with y and x. We're just using p's and v's. Okay, so this is the transition bit here that I think might be a bit tricky. Okay, when you get a basic equation like that, to recognize that because c is a constant, v is going to be changing because of whatever p does. So in other words, v is dependent on p. So it's just like this idea. Okay, there's no doubting you understand that. The fact that you throw in a 1 on x isn't such a big deal either. You're understanding that. Okay, so I shouldn't put that, I should put a comma. So some other version of that shouldn't be a problem either. So that's why I'm okay with you seeing this. Now, when you change the pronumeral, that can be a pest, because that there is all well understood, it's well ingrained, but then to get it in this term is a bit tricky. So if I want to differentiate that, I would say, what am I differentiating? I'm differentiating V with respect to P. Differentiating V with respect to P. So that would mean I'm writing dV dP. In the same way that if I had y equals c over x, see, this is where, if you've been taught to just do that, that's wrong. But if you've been in the habit of writing Leibniz notation, that transition now makes sense. And if you're practiced at that, this is not such a big transition either. Is that where it's coming together? Okay, now that's alright, that's here. Okay, so this is pre-work, right? When I do this, I say before we go ahead and invoke the differentiation rule, we have to rearrange this. And so what I've done is taken, whenever you have something on the bottom of a quotient, okay, one way to get rid of this is to have it brought up to the top, and you use a minus index. Now what's the index on the square underneath this one? It's invisible, isn't it? We don't normally write things with a 1. We could write any number, right, with a 1. But we don't do it. So the fact that the box is sitting there, it's got a 1. So in actual fact, that's what its form is. Now in calculus training, you should have had the gymnastics training, which says, oh, that's all you're doing. You're taking that and you're generating this one. Now the fact that we're doing it with numbers or pronumerals is irrelevant. So this minus 1 is the pre-work to rearrange. This is just rearranging. Nothing fancy. So that P, which was on the bottom of a quotient, on the bottom of a reciprocal, is being brought up next to the C, and to show that it was down the bottom, we put minus 1 as an index. Now we've got to go ahead and do the differentiation. So is that step to that step okay now? Alright, and then we go ahead and do the differentiation. The minus 1 comes out the front, times by C, times by P, and minus 1 gets a 1 taken off it. So minus 1 times C times P. Now minus 1 times minus 1, minus 1 minus 1 is minus 2. That's where the minus 2 is coming from. The result of the, so that's minus C, P to the minus 2. Now what does the minus index mean? We just discovered it up here. The minus index means now we're going this way. Right? If P had a minus, P should be down the bottom. P's got a minus, should be down the bottom. So let's put it down the bottom. What's missing? What's missing? The minus put it down the bottom. The index is missing. Okay? It's the change of pronumerals, I'm certain of it. Yeah, that's right. Alright, so in all of this, indexes and reciprocals are not well processed coming out of school. And as soon as there's a change of pronumeral, it's a big deal. Alright, so we've done a few of those. And we've done some of the other ones as well. What else did we want to look at? Anything? Now, I didn't see Mary. I didn't see any mechanics type questions in there. All right. So I think what I'll do, I'm going to go to the Maths Study Centre website and just have a look at those. Resources, under resources, library, math modelling for science, some worked examples, and implicit related rates and newtons. I'm going to go and open that. Alright, so that's implicit, and implicit's used in related rates sometimes. Okay, so this was a good one because it's a variation of the problem of the changing square, because you had a changing square that was quite simple. So I might just bring this out. Okay, so let's do it that way. Alright, let's do this one. So let's just blind ourselves to the answers. Now the length of the rectangle is increasing at the rate of 8 centimetres per second, and its width is increasing at the rate of 4 centimetres per second. When the length is 7 centimetres and the width is 6, how fast is the area of the rectangle increasing? Now I reckon that this is a great question, and the reason that I like it so much is because on one level it's a simple thing related to you know, related rates. On another level, it's complicated by the fact that we're trying to find rates at different points in time. So that's the beauty of what we're learning about in this particular topic. Okay, so let's just put our heads together and see if we can't come up with a solution for that. Alright, so what rates are we given, if any? So that's where you always start, isn't it? What are the rates from the words? Okay, what's dw dt? So that's the width. What else are we given? Terrific. dl dt. Okay, and what else do we know? Okay, so it wants find. So see how what we're doing is we're writing the damn question. We're writing the question because that's what you've got to do with these. So it wants the area, it wants dA dt when L is equal to 7 and W is equal to 6. Okay, So that's the mathematical information that we have. Now, what information do we have? What's the question about? What's the geometry? What's the geometric shape? Excuse me. What's the geometric shape? A rectangle. What's the area of a rectangle? Very good. Now, does that help us? What are we being asked for? Okay. So how are we going to get it? So what we're going to do is we're going to look at this bit. We're going to DDT this thing. Okay. Now this turns out to be quite a tricky question, because that requires us to conjure d82 when it didn't exist, to know that we had to conjure it when it didn't exist, and in the other problems that you got, it was always in the right part of the chain. It was volume with R, so dVdr. It was just slotting straight into the chain. These guys here aren't going to slot straight into the chain. You're going to have to conjure them. So this is the tricky part of this, even though it's a simple rectangle question, for heaven's sakes, and it wants to know, you know, this is the tricky bit. So how would you have known that? Well, just through a bit of practice, and let's have a chat about it. Alright, so what we want to do is do DDT on the left hand side of A, and we want to do DDT of L times W. Okay, so this one's going to give us d82. That was good. But we need to now do this. Now DDT with respect to t, where L and W are not anything to do with anything. So we have to treat them, we're going to differentiate them both. What's the problem with differentiating them both with respect to t? What are we differentiating? What's the term? We're differentiating A. Is it a sum? We're differentiating a product. What do you do when you differentiate a product? You have to use the, yeah. So this is a product rule. The fact that it's hidden inside implicit isn't the point. So we're going to have to assign U and V. That's going to be interesting. So let's have a look at that. So U equals L. That means U dash is going to be DDT L. That doesn't work. V is equal to W. V dash is going to be DDT W. Well, that doesn't work. It's like constant. No, it's implicit. Be careful now. Okay, be careful. So, how do we get it so that it makes sense? We do what? What's our biggest partner in differentiation? So we're still going to do d dt. We're just going to go through something else. What's the something else that would make sense here? So we're going to do that. We're still going to have d dt for L, but now we're going to have DDL. That makes sense now? DDL makes sense. So DDL's up here. Ah, okay. So that's what's going on. So what is DDL of L? What's DDL of L? What's DDX of X? It's just 1. And remember, we've got dl dt. So u dash is just dl dt in this example. Alright, let's go back up here and do this one. V dash. Well, that doesn't work. ddt to w doesn't work. We're still going to have dt dt for w, but we've got to go through something else. So what's the something else that would make sense? Brilliant. Now that that makes sense, what is the differential of dww? Okay, and we still have dw dt, and so that is v dash. Okay, so given that we've got that now, we can put this together as u dv plus v du. So we'll get u was L, v dash is dw dt, v was w, and u dash is dl dt. And all of a sudden we have a rate that makes perfect sense. Okay? Now the length that we were interested in was 7. The width we were interested in was 6. 7 and 6. Now dw dt was given as the width is increasing at the rate of 4. And the other one was increasing at the rate of 8. What's that? 8 and 8, 16. 676. So the area is 76 meters squared per second. Now that's a simple one, but it's made harder by the fact that you've got to use the implicit. So when things don't make sense, they do. It's just that. So hopefully you'll get the other ones where they just come out. But if they don't come out, what's that a clue? So when we're up here, what's that a clue to? When they don't come out, that is, it's not just a straightforward dA. What's that a clue to tell you? You've got to do implicit. Okay, so when they don't jump out at you like these previous guys jumped out, even that one was a bit annoying, but it was still there. I think this was a better one. They were there, weren't they? The volume R thing, so it was all there. Alright, so let's have a think about a harder one. Can I move on? Alright, so this is from the website again. An upright tank. So we've got a rate. So now your training should be, okay, what's the rate? So there's another question about a rate. Is the height. Ooh. Okay, so how fast is the height of the water increasing? So the tank, we'll assume, is a radius. And it's got a height. So what's the volume? An area is pi r squared. And a volume is equal to the area times the height. So that's pi r squared times h. Okay. So if we were to differentiate this, we would get dv d what? Whoops, there's no t. Where's the t? The t's missing. The question's asking for what? What's this question? How fast is the height? So how would we write that? Dh dt. So the question wants us to find dh dt. There's no t in here anywhere soon. So what's that, the trigger? That tells us use implicit. Okay, so to use implicit, what we'll have to do is d dt, which is what we want, v equals pi r squared h. Now r is 5, so r squared is equal to 25. We'll just put that aside. So each of the terms we get a dv dt, we get d dt pi 25 pi h. We're still going to have d dt, and we're going through 25 pi h. What would be an appropriate thing to put there to make that work? We would need to use dh. So we've invoked the chain rule and we've got our parts here. So this now makes perfect sense. So dv dt is equal to ddh 25 pi h, and we've got a dh dt left over. Now 25 h, so what's this one now? It was given to us. Yeah, so you're saying we have an answer for the left hand side of the equation. We still don't know what h is. Yep, and we're trying to work out this height. So there'll be a bit of equation shuffling to get this expression here by itself. We'll have to make that the subject. But this question still goes, what's ddh 25 pi h? ddh 25 pi h is, thank you very much. So what we'll do now is we'll divide both sides by pi and 25. And our rate, which is the one that we wanted, the height related to time, is 3 over 25 pi, which is a pretty small number. It's got 75, it'll be 3/75, so it's pretty small. Okay, so ddh dt. Now if there's any information on there about decimal points and the like, you've got to be careful that you respect that. So 3 divided by 25 divided by pi. So 0.038, 0.0382. We'll do the same as the statisticians, we'll do it for decimal places. So that's the rate of the height, millimeters per second. And that's it. So that one, again, was a bit tricky. Now there are a few of them floating around like that are a bit tricky. And you get to a point where you draw a blank because there's, how do I do that? Then yes, you invoke implicit and you invoke the chain rule. Okay? This was here. So I'm going to keep writing that up because how do you do implicit? You invoke the chain rule. Okay. Alright, any questions about that? Alright, now I want to check your you've got to recommend. Okay, so Stuart's still being used. Look, I really recommend to you, I know you don't want to hear it from a maths teacher, but just save the money up and buy the book. Whether it's the e-version or not, it's worth it. Okay, so textbooks, I've got my copy, which is worth it, and I know it's a lot of money. It isn't cheap, but it is really, really worthwhile. Okay, so if I have a quick look on here for related rates, there'll be more practice. There you go. So related rates, and it's exactly what we've been doing. There's a reading for you, and there's some practice questions there'll be. And so, man, if I was your lecturer, I'd be pulling questions out of here. Okay, filling a tank with a funny label. So that'll have, now you should get those. Spend time here with me, hopefully you're able to just get those now. Some problem solving, some examples. Okay, so I would encourage you to play, oh, look at all those questions. So, you know, that's how you win. You just get it, get the technique. You've had the training now, so now it's just a case of going and applying yourself. Okay, so that's a big section there. Plenty of practice for you to really become a genius at it. And what was the other thing that we were looking at? Newtons. Okay, Newton's method. Let's try that. No, doesn't like it. Alright, I might just come way down here. Don't know what I'm doing. You've got all your vectors and stuff on there as well. Yeah, that's interesting. That was interesting. Okay, so if you want to read up about Newton's method, applications of differentiation, it's on page 312, also called the Newton-Raphson method, and it's about finding roots. And guess what? There's plenty of examples and lots of opportunity for you to do some practice and get a feel for what it's trying to achieve. that's an example of the one that we looked at, which I'll write up before I post that. Okay, and there's lots of questions there as well. Okay, alright, so lots of resources for you if you really want to get into it. So hopefully you've been helped today. I'll go up and have a look at that other problem and fix that up before I post it. And then, what are we at? We're about 1:36, so we're going for a while. We might call it there. What do you reckon? Alright, thanks very much, guys. Alright, all the best. Thank you. Bye now.